All right, ladies and gents. Okay, so we are doing the second part of 2.4, 2.5, which is exponential functions. Okay, again, our objective for today as well is that students will be able to understand exponential graphs and their properties and use and apply exponential functions to real world scenarios by completing practical applications. So we're going to be talking more about the exponential graphs today and some of the properties. We're also going to be talking about the real world scenarios here. Okay. So now, quick review. Okay, we do have our exponential model here of f of x is equal to a b to the x power. Okay, when we have growth or decay, when we talk about exponential growth models or exponential decay models, our b is written as 1 plus r, where we have r is our rate of increase in a growth model, right? This is what makes b greater than 1 in a growth model, because we have the 1 plus that growth rate there. Okay, and then we have our decay, exponential decay model, and now we have our b is represented as 1 minus r, and this is r is our decay rate here, right? And this is what's going to make our b less or greater than 0 and less than 1, so between 0 and 1 there, okay, because we're subtracting the decay rate from 1. Okay, so then this brings us to our graphs. Okay, if you guys remember, this is going to be a little bit about like the differences in the graphs and transformations of graphs. So when we take a look at this, you want to pay attention to the different transformations and such. So over here we have, how do you find the differences between the functions of these two graphs? Okay, so you want to kind of check out the differences here. Remember that we have our function f of x is equal to a b to the x, okay? And in a situation like this, it's actually really important to remember one little tidbit here, okay, that a is actually the y-intercept. It's our starting point, right? Because if I were to do f of x is equal to a b to the 0 power, right, which is in our y-intercept, it's always 0 comma something, right? This 0, when we plug it in for x, no matter what b is, right, this is going to become a 1. No matter what b is, anything to the 0 power becomes 1. So this just becomes a, right? So when x is 0, we get our y as a. So our y-intercept is actually the point 0a. Okay, in a non-transformed variation of this. So when we take a look at these graphs here, we can see this is an exponential. Is it growth or decay? What are we seeing there? Is that a growth or decay? Okay, I got 2 responses there, 3, 4, 5, good. Good. All right, very good, guys. So that is an exponential growth here, right? We are getting larger as we move toward the right, okay? So that means our b is going to be greater than 1. The question is what is that b going to be? So we can actually take a look at some of the points here. Okay, we see that our y-intercept here is at 0, 1. Okay, and then if I take a look at my graph here, I can see maybe at 1, I hit a 2, and at 2, I'm over here. At 3, it's off the chart, so I'm not going to go there. Okay, so my points are 0, 1, 1 comma 2, 2 comma 4. So if I wanted to figure out my b, I could easily just do the division of the y's. So I could do that, right? So over here, I can do in my t table, I can say, okay, so when it's 0, it's 1, 1, 2, 2, 4. My x's are moving in the same increment, 1, 1. So I can do 2 divided by 1 is 2. And then 4 divided by 2 is 2. That means my b is 2. Okay. And my a right here, this is going to be my a. So my graph, right? Find the function of each of the two graphs, then compare them. My graph here is going to be, or my function is going to be f of x is equal to my a, which is 1, times my base 2 to the x power. Which literally just simplifies to 2 to the x power because it's 1 times that, right? Doesn't change much. Okay. On the other hand, let's take a look at this graph. Can anyone guess? I mean, we've had algebra too, right? Can anyone try to take a guess as to the difference between this graph and this graph? What kind of a transformation are you thinking you're seeing? Let's see if we can recall some of our vocabulary from last year. Okay. Okay, thank you. Reflection, reflect, reflection, reflection. Yeah, it is a reflection across which axes though? You want to be specific. Aha, thank you, Kai. Thank you, Juan. Reflection over the x-axis, reflection in the x-axis. Very good, Kai and Juan, okay? So yes, we have a reflection in the x-axis. Do you guys remember what that normally changed? Or what? How did that reflect in the function? Was it the a, was it an h, or was it a k thing? If we had a reflection in the x-axis. Okay. It's okay if we don't remember, but if you do, go ahead and put that in the chat. Uh-huh. Good. Good, Ariana. So it is in the A, but let's see how that shows up here, right? So we have that reflection. And we can see here now our y-intercept is at 0, -1. Right? Already we have that negative playing in there. If I go to 1, I'll be at, this will be a 1, -2. At 2, I'll be here, and this will be a 2, -4, okay? So the question is my base negative as well, or is it just the A? So if I take a look at my x comma y here, right, or x comma f of x, I have 0, -1, 1, -2, and 2, -4, okay? So if I do the same thing as I did on the left here, I'll have a -2 over -1, which is a +2 for my b. -4 over -2, again, it's a +2. So my b is still a +2 for my graph. So if I have my f of x here, my b is still a +2, okay? What changes is my a here. So that means now my a is -1. And notice I have the 2 to the x power all in parentheses and then the -1 on the outside. Okay, that's very important because the -1, you can't multiply into the 2 because the 2 is being raised to the exponent, right? So, and you guys are absolutely correct. This is a reflection over the x-axis. So we can say that graph 2 is a reflection over the x-axis of graph 1. Okay. And you guys already kind of answered the next questions. It says label the above graphs as as exponential growth or decay and justify. Okay. So graph 1 up here, you guys already named as exponential growth in the chat, right? Many of you, at least 6 of you, said that this was growth. So graph 1 here is exponential growth. Can anyone explain why? Why did you say that it was exponential growth? Okay, I have Juan's answer. Okay. So do me a favor. If you agree, oh, the y is doubled. Good. If you agree, can we all see Juan's answer in the chat? If you agree with Juan's answer, give me a thumbs up. If you have something different, give me a thumbs down. All right, very good. I like that. Okay, so we have a unanimous agreement. Okay, so yes, we have exponential growth because we can see that as x is increasing this way, so is y here, right? So we can say as x increases, y increases. Okay, can't see that. And yes, of course, Oswaldo brought up the fact that y is being doubled, okay? So, and we can show that, right? So we can say that y 2 to the 1 power is 2, but if I increase my x and I put like, let's say 2 to the 5th power, then I'll have like 32, right? So it's increasing as my x is increasing. Show an example of that. Now here's my question for you. What about graph 2? Is graph 2 growth or decay? Think about that. I'm going to give you guys a moment to think about that. Is my graph 2 growth or decay? Remember that decay, right? As x is increasing, y is decreasing towards 0. Y is decreasing towards 0 or asymptote. Think about it. Growth or decay? Okay, I have 2 opposing answers in the chat. I have 2 opposing answers in the chat. Let's take a vote. If you agree with Kelly that it's decay, give me applause. Give me a clap, like the 2 hands clapping together. If you agree with Kelly that it's decay. If you agree with Oswaldo that it's growth, give me a thumbs up. So thumbs up for Wally, clapping for Kelly. Come on, guys. I want participation from everyone. So, except Kelly and Wally, obviously, but interesting. Very interesting. Okay, okay. So the majority agree with Kelly that it's decay. That's an interesting. Only Anthony agrees with Oswaldo. I see where you guys are coming from. Okay, because your y is decreasing, right, toward the negatives. In a real world situation, this would never happen, obviously. This is more of the abstract mathematical idea of an exponential graph because, you know, in the real world, we're either getting bigger numbers toward the positive or smaller numbers in the positive, right? The majority of you are mistaken. Sorry. Okay. This is actually a growth model. This is actually exponential growth, but we don't just call it exponential growth. We call it a negative exponential growth. And the main reason that it's a growth is because your y's are still the absolute value of your y's, right? The absolute value of your y's is still getting larger. It's not getting smaller towards zero, right? So even though we're increasing in the negative, which we know and we have been taught that in larger numbers in the negative are technically smaller, right? But as far as exponential growth and decay is considered, right, we're looking at, are the numbers getting smaller towards zero or getting larger away from zero? And in this case, they are technically getting larger away from zero, which would still make it a growth, but it makes it, because it's reflected, it would be a negative exponential growth. Okay, so over here, we can say this because we can say that as x increases, the absolute value of y increases, right? The absolute value of the y increases. By the way, thank you for that. That was an awesome discussion. Well, reaction, I should say. Not discussion, but reaction. For sure. Thank you for the participation, guys. Doing splendidly. Yeah. So if I take a look at this example, y of negative 1 times 2 to the 1 power, that's going to give me negative 2, which the absolute value of is 2, right? And then y equals negative 1 to the 2 to the 5th power will give me a negative 32, which the absolute value of will then give me a 32. So we're still increasing technically. Still increasing the amount of our numbers, okay? All right. So then I can take a look at this guy, okay? So we have our asymptotes. Exponential functions always have asymptotes. And unless there is a change in my k, unless there is some sort of transformation in the k. So if you guys remember, right, we have f of x is equal to our transformation, a times b to the x minus h up here plus k. So if I had a plus k, then my asymptote would change from that y equals 0 line here. Okay, but until I have a k, the asymptote here for an exponential function is my x-axis here, okay? So remember that our asymptote is the imaginary line, vertical or horizontal. It could be slanted too, but usually it's vertical or horizontal. that a function can get infinitely closer to, but never actually touch, okay? It never actually touches our asymptote. So in this case, our asymptote is the line of y equals 0, okay? So we have find the equation of the exponential graph and label it as growth or decay, identify the asymptote. Okay. So what do we have here? Okay. Looking at our, what do you guys think looking at the graph already? Growth or decay? All right. Yes. Yes, yes, yes. Absolutely decay. Hey, great job, guys. I saw Lumeria, Kelly, Nick, V2, Wally, Juan, Anthony, okay, all of you guys, well done. Okay. Yeah, for sure decay. So we know that this is an exponential decay. So now the question remains of like what's the actual equation, right? What's the function? So we got to take a look at our points again here. So I have that one there, and I can probably name that as a 0, 1, right? A 0, 1, because it's not labeled, so I can label it as 0, 1 if I wanted to. So my X point here, X, Y, all right, 0, 1, that's my guy right there. Let's look at 1 over here and this point right here. What does that look like? Does it look like, that looks like about half, right? So when I go to 1, I have about a half. And then it's going to get increasingly more difficult here. But if I go by this pattern, right? If I go by this pattern, then at 2, it's going to be a 1/4. Okay. Which means my B, I can do 1/2 divided by 1, right? I'm dividing my Y's here, which is going to be 1/2 either way. So my B here is 1/2. My A, right? That's my A. So my function can be f of x is equal to 1 times 1/2 to the x power. All right, there's my A. There's my B. And this is increasingly moving toward my asymptote here. So let's take a look. Okay, over here, let's see. This is 1, 2, 3, 4, 5. So let's take a look at 5. What would my y be when my x is 5 for this function here, 1/2 to the x power? So if I do 1/2, okay, oh, you can't see that, my bad. 1/2 raised to the x power. So in this case, I'm going to do to the 5 power. That becomes a 0.03125, okay? I want to show you here as a function, 1/2 to the x power, okay? As a function, I can do table, so I can do second graph, but instead of graphing, it gives me the table here. Look at my numbers as my x is increasing. Okay, look at my numbers. So on the negative side of x, I'm up high. And then as I go, my numbers are getting smaller and smaller. This is scientific notation. Did you guys ever learn scientific notation in chem? I think it was chemistry. Okay, scientific notation, yeah. So this is 9.8 to the -4 times 10 to the -4 power, right? That means move this decimal 4 spaces to the left. Move that decimal 4 spaces to the left. Watch how this is going to increase now. So what this means is as my x gets higher, there's more zeros after my decimal before I hit another number. Okay. There's more zeros after my decimal. Look at that. That is going to be 0.000000000000000000006. Very itty bitty. Very itty bitty. Okay. So it's getting closer and 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 closer to zero, but it's never actually going to be zero. It's just going to get very, very, like, even this, you're never going to see it actually say zero as I go. It's like, look at that. I mean, effectively speaking, in the real world, that is the equivalent of zero. But it's not going to actually tell you zero because it can't be zero. Why can't be zero? Isn't that crazy? But if I were to graph this, I mean, you see it hit the asymptote, like you're seeing it skirt around there, right there. So like if I were to change my my window and I were to put like my X maximum, like go up to 500, right? If I were to go up to 500 and let's say I was moving by tens so that it's not that crazy of a thing. Look at this. Oh, I can't even see my graph. Interesting. See, on the graph, here's the problem. On the graph, it actually gives you y equals 0 when you're tracing it. But on the table, it won't, because the table will actually give you like the minor details there, right? Here, let me go something smaller so we're not that crazy. Let's move by 5s. Nope. Graph. There you go. I actually want to go on the, oh, I'm not able to trace the function itself. Hold on. Oh, I thought I was tracing the function before. My bad. I was not. Okay, never mind. But you get the idea. So if you ever want to see the table for your function that you put into here, second table, and it should give you your X and Y values right there. Okay. And then I'm going to second quit to get out of that. Okay, moving on. Okay, that's our decay model there. And of course, we're going to write down that our asymptote here is our x-axis, aka y equals 0. Okay. All right, let's flip over. Give you guys a second to finish writing that. Okay, let's take a look at these two guys here. It says, given the following graphs, find the asymptotes for each, and then use that to help you formulate the equation of the function, okay? So over here, we're really talking about the translations that are taking place, right? So let's, again, I'm going to remind you guys, remember our transformations. F of x equals a times b to the x minus h power okay, plus K, right? Where K is what's going to change our asymptotes here. And this, from K is going to change our asymptotes, like our up and down asymptote. And H is our right and left, right? H is our right and left here. So I'm going to just say, let's suppose that each of these are the parent function is f of x is equal to 2x, okay? Let's say the, the starting function, the parent function here is f of x is equal to 2x. Okay, so then what's the changes that are happening in graph 1? Let's take a look at that one. Okay, where did our asymptote move? Okay. So we can see here that this line did not go past, our graph did not go past this line right here. It just kind of skirting along it, right? So if it was going to pass it, it would have passed it a long time ago. It would have passed it like somewhere here. But it's just kind of skirting along, which means that our asymptote has moved up to this spot right here. Well, this is 1, 2, 3. This is the line of y equals 3. Okay. Which means over here, we had a vertical translation, okay, of 3 units up, i.e., we have a k equals positive 3 situation. As far as we can tell, there was no movement right or left. So that means our transformed function would be 2 to the x power and then plus 3 on the side. Okay. We could also see that from here as we look at this y-intercept, a 0, 4. Okay, 0, 4, which means that our initial y-intercept for the 2 to the x function, which was 1, increased by 3, right? So if I take a look at this y-intercept here, right, that was a 0, 1. So it started at 1. So in order for it to get to 4, it increased by 4 there, okay? All right, so if we take a look at graph 2 though, I'm seeing that my asymptote probably hasn't changed. It's still kind of hitting at 0 there. So there was no vertical translation here. Although it does look like there was a horizontal translation here, right? The question is how much? How much did it translate? Our asymptote might help at this one as well, okay? So usually our asymptote was at 0, 1, right? For the original parent function. Now I want to see, okay, what x is 1 at? What x is my y 1 at? So that's going to be right here. That looks like it's at -3. Okay, which probably means that my entire function transformed 3 units to the left. Are we following? So I'm using my y-intercept here, right? My y-intercept is at 0, 1 for the parent function. But now I get 1 when x is negative 3, which means I had a translation of 3 to the left here. Okay, so that means that we have a horizontal translation of 3 units left. Okay, we had a horizontal translation of 3 units left, which means our h is equal to negative 3. So using our function, that means that h is going to go there, right? So I have f of x is equal to 2 to the x minus a negative 3, right? The minus, this minus comes from the actual form. This minus 3 is the actual h, which simplifies to 2 to the x plus 3, thus reminding us that h in here, in the function, h lies. Okay, let's go on to bacteria. Okay, any questions on the translations before I move on, actually? Give me a thumbs up if you're good so far. Thumbs down if you have questions. Thumbs down, I'm sorry, thumbs up if you're good so far, thumbs down if you have questions. Okay, can I get a response from everyone, please? Kai, Wally, William, Don. Can I get a response from everyone, please? Thumbs up if you're good, thumbs down if you have questions or need some more explanation or anything of that nature. Okay. Wally and Will. Guys, if you need if you're gonna take a bathroom break or anything like that, please put the little time thing that says that you're away so that I know that that's why you're not responding and it's not just because you're done paying attention. Okay. I need some sort of indication. If you're step away from your computer, let me know that you stepped away so that I'm not taking away participation points from you. All right. Okay. All right, good. Let's take a look at some of the bacteria. Okay, so all thumbs up, we're good to go. Let's move on. These are the real world examples that we wanted to talk about where exponential growth and exponential decay can be used to help us. So I've mentioned a few times that a lot of exponential growth or decay can be used in the medical field, in the science field, okay, with a lot of bacteria growth or half-life stuff. Okay, half-life is usually used with chemicals. So they'll use half-life and exponential decay to talk about to calculate how long it'll take a place that was maybe affected by a nuclear bomb or a nuclear spillage or some sort of nuclear issue that is, radiation. So radiation has a half-life, right? And so they can use exponential decay models to calculate how long it would take for that area, that space, to be safe for humans to go near again, okay, without getting radiation poisoning. Another way that exponential functions is used in the medical field or the science field is bacteria. Okay, it says bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells. So multiplying, splitting into cells, we're talking about exponential growth, okay? So every bacteria splits into 2 new cells, okay? AKA it's doubling. If we start with only one bacteria, which can double every 30 minutes. How many bacteria will there be by the end of one day? Okay. So the initial statement is giving us our B. It's giving us our growth. Okay. Can anyone figure out what our B is going to be? Our growth. I don't want to say growth rate because that's the wrong term, but like our exponential growth factor. There you go, the growth factor. Okay, if every bacteria is splitting into 2 new cells, aka doubling, what would your B have to be in order to double? Oh, I hid the chat. No. B is not. Remember, B is not our variable. B is a number. X is our variable. X is in the exponent. Okay. So not B squared, but B itself is 2. Right? So the fact that our bacteria splits into 2 new cells, aka double, that tells me that our B is 2. That gives me my growth factor right there. Okay. It says if we start with only 1 bacteria, what information did that just give me? We start with only 1 bacteria. We have our B, okay? What information did that just give me? So we know our B equals 2. In a function like that, which one determines the starting point, the starting number? Oh, I'm sorry, I wasn't looking at the chat. Yes, that gives me the A. So then what does it tell me? It's telling me that A is equal to what? 1. We start with only 1 bacteria. That means A equals 1. Okay. So the function I'm looking at here is f of x is equal to 1 times 2 to the x power. Okay. Then they give me some timelines. Okay. They're telling me that we start with only 1 bacteria, which can double every 30 minutes. So it doubles every 30 minutes. Okay. Which means that our each value in our x, right? X equals 1 means 1 30-minute interval. X equals 2 means 2 30-minute intervals. So our x represents the number of 30-minute intervals. That's what our x represents. Okay? Because it doubles every 30 minutes. So this action takes place every 30 minutes. They want to know how many bacteria will there be by the end of one day. Okay? By the end of one day. So we got to figure out how many 30-minute intervals there are in one day. Well, one day is 24 hours. Right? And every hour, right? Every hour has 2 30-minute intervals. Right? There's 2 30-minute intervals every hour. So in 24 hours, 2 30-minute intervals per hour, that's going to be 24 times 2, which is going to give me 48 intervals. Okay, so that means my X at the end of one day will be 48. So how many bacteria will there be by the end of one day? Well, let's see. That's going to be F of 48 because I'm plugging in 48 into my X. So this will be 2 to the 48 power, which is handy dandy calculator. Remember, that's not 2 times 48. That's 2 to the 48th power. So 2, my little caret here, 48. You ready for this? Okay. Gave me scientific notation. So let's see here. Okay. It's 2.814749767 times 10 to the positive 14 power. Okay, so that means move my decimal here 14 places to the right. So for here, that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. My bad. 9 to get to the end of 7. So this is going to be 28147497767. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So every 3 numbers, putting in a comma here. So that's hundreds, thousands, 100,000s. No, sorry. Hundreds, 100,000s. That millions, millions, billions, trillions? 281,474,976,700,000 bacteria by the end of one day. And that's starting off with 1 bacteria, y'all. 1 bacteria. Oh boy. So, word problem deserves a word answer. So there will be 281,474,976,000,000. Oops, I wrote that too high up. 700,000 bacteria by the end of one day. Eesh. Yeah, that was fun, huh? Wash your hands, sanitize, wipe things down, please. This is very timely with COVID. Okay. Any reactions to that number? Any reactions to that number? Yeah, that is a lot. It's a lot. Most definitely. Yeah, but virus spreads very similarly as well, Kelly. They might not multiply as quickly, but they do multiply similarly. It's just a matter of how it's spread. Right? Coronavirus is airborne. Bacteria can be spread off of surfaces. So can coronavirus, actually. Yeah. So you got to be careful. You got to be careful. All right. Let's take a look. It says each year, the local country club sponsors a tennis tournament. Play starts with 128 participants. During each round, half of the players are eliminated. How many players remain after 5 rounds? Okay. Let's read that again. Each year, the local country club sponsors a tennis tournament. The play starts with 128 participants. During each round, half of the players are eliminated. How many players remain after 5 rounds? Okay, I'm going to give you 1 minute, and I want you guys to determine out of this statement, these statements here, what's my A and what's my B? What's my A and what's my B? I want participation from everyone, please. Please. Read it carefully. Remember, A represents our starting amount. The B represents the rate at which, or the factor at which we are growing or getting smaller. Okay, so I see that there's a consensus that A is 128. Yes, we are specifically told that play starts with 128 participants. Okay, so that's going to be our A. Our B is the rate at which, in this case, we're getting smaller. The rate at which the players are being, like, after each round, right? What's the rate at which they're getting, the group is getting smaller? Okay. So it says right here, during each round, half of the players are eliminated. So then what's my B? 1/2. Or 0.5, however you want to look at it. Okay. It is my, in this case, decay factor, right? Because I'm getting smaller. The group is getting smaller here. So it is my decay factor here. Okay. Now, after 1 round, right, we can calculate the 1 round, each round, right? X in this situation represents the number of rounds played. X represents the number of rounds played here because we want to know how many players remain after 5 rounds, right? So if we're talking about 1 round, right, then we would do 128 times 1/2 to the 1 power. But we need to know 5 rounds. So our function here is very simply y, or f of x, but y is equal to 128 for my A, okay, times my decay rate here to the x power, where x represents the number of rounds played, right? Remember, it's not an exponential function if your x is not in the exponent. If your x is not in the exponent, you ain't dealing with an exponential function. Okay. So after 5 rounds, we can figure this out, right? That's going to be y is equal to 128 times 1/2 to the 5th power. So grab our handy dandy calculator. 128 times 1/2, or if you really want, you can put 0.5, which is totally fine. raised to the fifth power. So remember that it's only the 0.5 that's raised to the fifth power. Hit enter, and we get 4. So we get that y would equal 4, which means that after 5 rounds, there will only be 4 players remaining. So essentially, we'll be in the semifinals, right? After 5 rounds, there will only be 4 players remaining. Okay. Alrighty. Ready to move on? Okay. So this next one here, okay, we got one more example. I want you guys to try this one on your own. The pesticide DDT was widely used in the United States until its ban in 1972. DDT is toxic to a wide range of animals and aquatic life and is suspected to cause cancer in humans. The half-life of DDT can be 15 or more years. Half-life is the amount of time it takes for half of the amount of a substance to decay. Scientists and environmentalists worry about such substances because these hazardous materials continue to be dangerous for many years after their disposal. If there are 100 grams of DDT, how much would be left after 75 years? Okay. So there's a lot of background knowledge here. Okay. One of the things about half-life is it's literally telling you your decay rate. It's telling you your decay factor. Okay. Half-life. What's going to be your B? What's your decay rate going to be if we're talking about half-life? Yeah, half. Okay. Now, this sentence is important, right? Because our B is half, but the half-life for this chemical happens every 15 years, which means your X is the number of 15-year intervals. Okay, the X is the number of 15-year intervals because it gets cut in half every 15 years. Okay, so I'm going to leave you with that. Figure out your A. And then tell me, answer the question. If there are 100 grams of DDT, how much would be left after 75 years? Okay. I'm going to give you guys about 5 minutes. Hopefully you guys can do this in 5 minutes. When you are done and you have an answer for me, do me a favor and give me a clap. Let's change it up. Give me a clap when you're done and you have an answer, okay? Clap, clap. Okay, so if you're still working, you can check the equation to make sure that you have the equation correct at least. Okay, still waiting for claps. Oh crap, I just erased all the claps. I'm sorry, can you put them again? I suck. So sorry. Give me a clap if you are done and have an answer. My bad. It happens. Oh, look at that. Got way more claps than before. All right. All right. Okay. Ooh. Good, good, good. Okay. We're waiting for claps for Ariana, Aaron, and Lumeria. So hopefully you guys are almost done. I'll give you guys maybe 30 seconds more. Eeny, meeny, miny, mo, catch a tiger by the toe. If you got it, let it go. Eeny, meeny, miny, mo. Ooh, okay. Juan, what'd you get, bud? Juan? I know you're there. You just gave me a clap, man.
Hello.
Yes, hi. I want you guys to talk because I want to hear your voice. Go ahead,
Okay.
Juan. Tell me what you got.
I like the whole thing, right? In like the word problem form.
Yes.
I said after 75 years, there will be 3.125 grams of DDT left.
Very good. So what was your X?
5.
5. Okay. So you did 75 divided by 15. Which got you 5. Okay. Okay, very good. Give me everyone in the participants window, give me a thumbs up if you got the same answer. That after 75 years, I'm writing down what Juan told me. After 75 years, there will be 3.125 grams of DDT left. Give me a thumbs up if you got the same answer. Thumbs down if you got something different and we'll figure out what went wrong. Okay, Lumeria, still waiting for a response from you, bud. All right. Anthony, you have a thumbs down. What's up? Let's help. How can we help? ¿Qué pasa?
Instead of 3.125, I got 250.
Okay, was your equation correct?
Yes.
Okay, when you plugged it into your calculator, can you read to me how you plugged it into your calculator?
I did 100 parentheses 0.5 0.5 to times 5.
Times 5?
Yes.
Okay, so that's where you went wrong, hun. So it should be 100 parentheses, right? So exactly how you did it. So 100 parentheses 0.5. Did you close the parentheses?
Yes.
Okay, and then instead of times, you want to do the little caret for the exponent, and then 5. So x is in your exponent, right?
Yes.
And then when you hit enter, you'll get that 3.125. But if you do what you told me, 0.5 times 5, right? Then you'll get your 250, because this isn't, so this is the same thing as when you raise it to the 5 power, it's the same thing as doing times 0.5 times 0.5 times 0.5 times 0.5. How many was it? How many was that? Hold on. That's only 4. One more. Times 0.5, right? That's what raising it to the 5th power does. It's you're multiplying it by 0.5 5 times. Whereas this, it's 0.5 plus 0.5 plus 0.5 plus 0.5 plus. Multiplication is just multiple addition, whereas exponents is multiple multiplication. Does that make sense? So that doesn't matter. And I don't know if I just went into a deep explanation just for like a minor mistake where you know that that was a mistake, but just wanted to make sure that that was clear. Okay. To end the day, I do want you guys today to do the summary because it's a really great question. It says, describe the difference between exponential growth and decay and when you would use each. Relate growth and decay to real life scenarios. Is it useful? Explain why or why not. Okay. And your assignment for the weekend is just to do homework number 10. We will focus on the class assignment in class. Okay, so I don't want you guys worrying about the class assignment as homework this time. I only assigned it last time because it was pretty short. But this time around, I only want you guys to focus on the homework number 10, I believe it is. Go to chapter 2 here. Okay, chapter 2, chapter 2, chapter 2. Here we go, yeah. Lesson 2.4, 2.5, day 2. So 11, 12, 2020, that's today. Okay, so you guys are just gonna be working on the homework number 10. All right, that's your homework. It is short. It's not that long. I don't think it's just one page front and back. It's word problems, exponential word problems. Okay. Yay. And if you have questions on it, make sure that you bring it to class on Tuesday and we can talk about it. Okay. Any questions? Preguntas, problemas, comentarios? Like I said, the classwork we will do in class together. So do not worry about that. We will figure it out. All right, kiddos. So So after you're done writing this up, okay, you are dismissed. Have a wonderful day. Have an amazing weekend because I won't see you again this week. Be safe. I care for all of you. And one more week until we have Thanksgiving break. Whoop, whoop. How do you calculate an increase of a percentage? Solid question. What question is that from, Nick?
Homework number 9.
Homework number 9. Okay. Which number from homework number 9? Help me out.
3.
Homework number 3. Says, Anna, are you talking about like the increase of 7%, the decrease of 2%, that kind of stuff?
Yeah.
Okay, so remember that they're giving you your growth rate or your decay rate, right? So you have to, you're using these guys. Your growth rate and decay rate or rate of increase and rate of decrease, right? That is your R in these scenarios. Do you see them?
Yeah.
Yeah. So if it says rate of decrease rate, then that's your R here. And remember that percent means you have to modify it into decimal form, right? So a 2% would be 0.02 for R. And then if it's an increase rate, then you're using this guy. And again, it's the same way of getting R. You're going to modify the percent into a decimal, but now if it's increase, you're adding R. If it's decrease, you're subtracting R. I hope that helps.
Okay, thank you.
Have a good weekend, Juan. Be safe.